Welcome to the last section of low vision. You guys are doing great. Let's finish strong. We're going to start this last section of low vision by kind of talking about just a little bit of some differences between a general eye exam and a low vision exam, right? We know that they're just a little bit different, aren't they? Whenever you look at a low vision exam, you guys see this in your text, a low vision examination. One of the things that makes it a little bit unique in terms of that compared to general exam is that one of the key things we want to know is what does the patient want in terms of their visual goals, right? In a general exam, that would be, I want to see everything, right? Because how many of us have had that patient that's like, I can't see that sign that's 10 miles down the road and I think I should be able to see it, right? So in a low vision exam, it's a little bit different because they're a little bit more realistic and they have specific goals they're looking for. I want to be able to read my magazine. I want to be able to see at the grocery store the numbers on the cost of the macaroni or whatever I'm getting. I want to see my TV better. Those kind of things. So a lot of times we start out by talking about what do they want out of the examination, and then that way it'll kind of tailor us to try and help them fulfill their needs, right? And so at the end of the exam, they feel like we really help them be able to meet whatever goal that they need to do. And we do that to a degree in general eye exams, but I think it's just even more important in low vision exams. One of the other real big differences between a general eye exam and a typical low vision exam, right, is that a general eye exam, we're typically going to refract the patient behind a phoropter, right? Whereas with a low vision exam, what are we going to do? We're typically going to use a trial frame refraction. So let's talk a little about that. So trial frame refractions, right? One of the key things we need to do whenever we're trying to do a trial frame refraction, especially with patients that have reduced vision, is figure out what is their just noticeable difference, right? What amount of lens change do I need to make so that they can actually tell a difference in their vision, right? Somebody that has a really reduced vision, if we make a quarter diopter change, they're not going to tell any difference, right? And so how do you calculate that just noticeable difference? Well, you guys see that here in the text, right? So just noticeable difference is the smallest lens change that a patient can detect. What you're going to do is you're just going to take the Snellen denominator, right, and divide by 100. Okay, Snellen denominator, divide by 100. So that's not necessarily in here in terms of an equation. So if you want to write out the side of this box, J and D equals Snellen denominator divided by 100. I think that'll be kind of helpful there. So we do have the example in that box of a 2400 patient. So what we would do is we take 400 divided by 100. You get 4 diopter lens change, right? So what we can do is we can show them plus and minus 2 flippers, right? Because whenever we have the plus 2 in front of them, will be 2 diopters over where they're at. And then we'll have the minus 2, we'll have minus 2 in front of them. So we'll have a 4 diopter shift, right? We could also show them like plano and plus 4 and plano and minus 4, right? Because that would be a 4 diopter shift as well. So any of those changes we've got in terms of the point, the whole big picture there is you want to make a 4 diopter shift to try and help them be able to tell whether there's a change in terms of their vision, right? That's going to be just noticeable difference. We also want to talk about eccentric viewing because that's going to be something that's going to be important for us whenever we're trying to do acuities on a patient that has low vision. So remember, eccentric viewing, different from eccentric fixation, right, which we'll talk about in binocular vision, right, a little bit later on. And we'll get a little more detailed into the comparison of these two. Remember, eccentric viewing is purposefully using a spot other than the macula, right, to view an object because a patient has some kind of macular disease, right? So what they're doing is they're going to look at the letter and then they're going to look off a little bit to try and find a spot that's a little bit better because they have a central scotoma or a central vision loss, right? That's going to be eccentric viewing. You guys will see that here in the text. All right, guys, let's talk about how do we determine the amount of magnification that's required for a patient. Right, so there's kind of a simple formula here to kind of give us a starting place, and of course we trial frame on from that. But you can think of, okay, what kind of distance magnification would be needed? Take what is their current visual acuity, right, and divide that by what they want to be able to see, right? So where they are, and then take them to where they want to see, right? That's going to give us our magnification needed. So you guys will see in the text, we've got an example here, 5.40. A patient presents with 2100 distance acuity. The patient would like to be able to read road signs, which requires 20/20 acuity. What kind of magnification telescope would be required? Right? So if you look at that, all you're going to do is take the 100, right, the denominator of the acuity they can see, divide that by what they want to be able to see, which is going to be 20, right, 20/20. So you're going to divide 100 by 20 is going to give you 5x would be your telescope that you would tentatively start with to try and be able to give that, or the magnification needed that you would be able to tentatively start with to try and give that patient the vision that they are trying to achieve, right? We also have a couple other formulas we want to talk about here. There's also a magnification of formula for near. It's essentially the same one. You take what they can see over what they want to be able to see, and then multiply it times the distance that they want to see that at. So that's kind of the only difference there. You want to do a working distance in meters, right? So example would be like using this example in the 5.4 example, a 2100 patient wants to see 20/20. Let's say they want to see it at 40 centimeters, right? So all you do is take 100 divided by 20, that would be your 5, multiply that times 0.4. That's going to give us 2x magnification we want to give that patient to try and help them see at 40 centimeters. Let's finish up this section by talking about Kestenbaum's rule and the lighthouse method. Both these, Kestenbaum's rule especially is kind of more of an estimate method. It's kind of like a starting place for us trying to figure out what kind of add power do we want to give a patient to try and help them see what they want to be able to see. And so you can kind of use Kestenbaum's rule as just inverse their visual acuity, right? And that gives you a tentative add that you're going to be able to give that patient. So in our example, we've got right below that, you see a patient presents with 2200 vision, right? Based on Kestenbaum's rule, what add would we want to be able to give them? Yeah, you just take 200 divided by 20, you're going to get a plus 10 add, right? So a plus 10 add is what we would want that patient to be able to use. That's Kestenbaum's rule, just inverse the VA. Like I said, it's more of an estimation method, but I want you guys to see that because it will be helpful in clinic to kind of give you a starting place to work with. And then it's also going to be something you might see on a quiz and moving forward. The one that's a little more accurate is probably the lighthouse method, right? And so that's where you measure the near acuity in M units, right? We talked about M units on the last section, right? Remember a 1 M letter, right, at 1 meter is defined by what? A 1 M letter at 1 meter is defined by a letter size that has 5 arc minutes total size, right? Good job. And 1 arc minute of detail, right? And so that's going to be equivalent to a 20/20 letter. Great job, guys. So that's kind of tying in some other things to that. M units, right? And we're going to measure their M notation or their acuity in M at 40 centimeters, and we're going to multiply that times 2.5. So that's the lighthouse method of calculating their near add needed. So we've got an example here as well. So a patient sees a 4M letter at 40 centimeters. What add would we tentatively want to give that patient? You take 4M times that 2.5 and you would get a plus 10 add is what you would tentatively want to give that patient in terms of an add power. So, all right, guys, you guys did a great job with low vision. You guys dominated this subject. Go dominate the quiz and we'll see you on the next video.